Thank you very much. It's really an honor to give this course, obviously. So thank you very much for the invitation. I'm sure I'll disappoint you. I'll do my best to minimize the damage. So one could say that this whole idea of singular support is technical. So it emerges from a rather fine point on homological algebra. So, and let me tell you the source, the origin. So there are these things called spectral sequences, and we're used to them converging, but sometimes they diverge. So the spectral sequence doesn't compute what you want it to compute. And so this whole idea of singular support is a measure to which a spectral sequence does not converge. And you may think, well, the spectral sequence doesn't converge, who cares, it's boring. But in fact, some mathematics does emerge from there. And I should say that it's not the first time. So the exact framework that I'll be discussing has appeared before. So one is, I'll mention it not in a temporal succession. One is what's called matrix factorizations. These things were discovered by physicists. So these people are smart guys. And another context was much, much earlier. So this is Tate cohomology. So they were also smart guys. And so, but it's the same idea of that we'll be dealing with today. So as I said, we'll be measuring the divergence of spectral sequence, and it's a kind of functional analysis. So we'll be doing functional analysis within category theory. So now, as to the framework of these lectures, today, well, let me say a sort of introduction. So Gelfand used to say that if you write a paper, the introduction must contain it all. So like you must say everything you want to say in the introduction, and then there are a few technical details left for the remaining 100 pages of your paper. So I'll basically try to say it all in one today, and I don't know what will happen. Okay, so let me begin. So, see, I already screwed up. No, I don't know how to lift it. This needs to go. Yes.
It's not by physicists.
Say again?
Matrix fixations are not by physicists. It's first by commutative algebra and then by meter.
Yes.
It's a problem here, so you should avoid
Yes.
use this one.
Yes. So, yeah, so all of this is joint work with Dima Rinkin. So for us, the motivation came from geometric Planck lengths. So let me begin from there. So X is a curve, a smooth complete over a ground field K. So K will be algebraically closed, characteristic 0. This is because mainly just because I'm a coward, I'm afraid of characteristic P. And G is a reductive group. So geometric Langlands begins as follows. You consider bund G. This is the moduli space of principal G bundles on a curve. And you consider the category of D modules on that. So derived category. Well, when you talk about geometric Langlands, 90% of the time you talk about this, but in this course we won't. So it'll appear as a motivation. So I won't spend much time talking about D modules and what this derived category means.